Hello, everyone. Thank you for joining me today. My name is Wyatt, and I'm a software engineer here on the Next.js team at Vercel. Partial Prerendering is an experimental rendering feature that we announced at last year's Next.js Conf. I've only been on this team for about 2 years now, but I've spent most of that time working towards its development. We're going to be taking a deep dive today into how it works, how it impacts site performance. It's changed a lot since we initially announced it, so I'm really excited to share with you now how it works. First, we defined the series of metrics that we use to measure the site performance, core web vitals, and how they guide our efforts in optimizing the user experience. Next, we'll discuss how Next.js renders pages today, what I'll refer to here as traditional rendering, and I'll break down the limitations of these methods and why balancing speed and functionality is a persistent problem for developers. This will lead us into partial pre-rendering. We'll cover how it works and what changes we've introduced since last year. We'll also cover the new async request APIs that you saw earlier today in the keynote and explain why they were needed and how they were implemented. We'll cover how to identify static and dynamic content, strategically use suspense boundaries, and leverage dynamic fallbacks. Looking to the future, I'll touch on how the planned improvements to PBR. Let's get into it. First, let's talk about core web vitals, what they are, how they measure the application performance. Core web vitals describe a series of metrics that provide us with a number that we can use to evaluate the experience for our users. The metrics that make up core web vitals are the largest contentful paint, interaction to next paint, and cumulative layout shift, quite the mouthful. Each of these can be measured and all include target values that help developers quantitatively measure how their applications perform. Today, we're just going to be focusing on largest contentful paint, as partial pre-rendering is uniquely designed to solve some of those problems. First, looking at time to first byte. This is measured from the request start until the first byte of the HTML document is received. It's a very important metric, as it's often associated with server speed. It's impacted by every layer of the network stack between the user and the server. The more layers we need to traverse, the slower the metric. Next, we have first contentful paint. This metric is also measured from request start, but finishes when any part of the page's content is rendered on the screen. This is very important as well, as it's associated with the user's perception of the loading speed of the page. If the time for the first contentful paint is too high, a user may think that the page is broken and leave the site. Finally, we have the largest contentful paint itself, or LCP. It's measured from the request start as well, but it's finished when the largest visible element is rendered on the screen. This includes any time it takes to unload the current document, set up connections, perform redirects, and of course, time to first byte. It's considered good to have an LCP that's less than 2.5 seconds, but that's a really long time. If users had to wait that long for pages to load, they might bounce and find another place to buy something from their store. Ideally, you should be targeting a number far lower than that, something in the realm of a few hundred milliseconds. With that understanding of core web vitals, let's discuss the challenges we face with traditional rendering approaches. In web development, as this isn't isolated just to Next.js, we typically encounter two different rendering strategies, static and dynamic. Static rendering is fast, but lacks request data. This includes single page apps. Whereas dynamic rendering includes request data, but can be slow due to server response times. This leads us to a critical question. How do we balance the speed of static and the functionality of dynamic rendering? Each has their own pros and cons, and choosing between them is often crucial to an application's performance story. Static rendering is known for its speed, where it can deliver the entire page from the edge. We avoid a trip back to the origin to get the initial HTML and can send it directly to users as fast as possible. Static rendering, however, lacks the ability to read request data, and instead has to retrieve the information using client-side requests, resulting in expensive round trips to the origin. In Next.js, when you want to access request data, you call one of the request data APIs, like cookies or headers. These are only available in server components, and once called, the entire page is marked as dynamic and is opted out of static rendering. With dynamic rendering, request data can be accessed, and HTML can be rendered server-side. This also means, though, that users are left waiting, as the network has to reach all the way back to the origin in order to render the first byte of HTML. This does mean, though, that we can retrieve the data needed to render our page faster, reducing expensive round trips, because we can retrieve the data right at the origin. Both of these approaches are what Next.js does today. But I've talked to you for a little bit while right now, and I'd really like to show you a practical demo, because if you're anything like me, an example probably helps. You could switch to the demo. So this is EcoStore. It's an eco-friendly e-commerce store. Quite the mouthful, names in progress. But in this particular example here, we have a lot of data that's representative of a traditional application that needs to load data from the server. We have product information, related products, a cart, add to cart, and oh look, information about what quantity is left available from the, oh, that didn't work, that's funny, isn't that great? Well, live demos be live. So what's really important to note as a part of this here is to understand the differences between static and dynamic rendering. To understand these differences, I've actually implemented both as a part of this demo. Right now we're looking at the dynamic version. We can switch over to the static version. And we can take a look at the static cart as an example. Right now, the static cart implementation uses useSWR. It's a hook that's designed to help you retrieve data client side, but it has a big disadvantage. We have to wait for the page to render and all the HTML to load into the page in order to make a request. This, of course, introduces a lot of latency into the process. While it does allow the rest of the page here to be static, which ensures that things like HTML, JavaScript, CSS, and fonts can load early, it does mean that loading the actual important pieces of the page takes some time to load. We're still able to present users with a loading state, which is fantastic. We never said Next.js didn't provide you with all these options, but we're looking to try and improve it. Now let's try and compare this to the dynamic version of this page. So you can already notice something a little bit different, because in this case here, this dynamic cart, that's a dead giveaway, but let's ignore that for the minute. And instead, let's focus on the more exciting bit, which is the suspense boundary that's wrapped around it. That's a really good indication that something dynamic is occurring inside of this component. That's because when we take a look at dynamic cart, it's actually an async component, and it calls await get cart. That's a good hint. Let's take a look. So in this implementation, it calls await cookies to retrieve the cookies from the request. We named it jar. We already took the cookie's name, unfortunately. But in this case here, the cart information is actually stored in a cookie, and we parse it and can retrieve the actual data from the database to present the products to the user, and returns it. And then we can pass that straight into our UI component, which displays the information to the user. This is fantastic because it means that we can retrieve all this data server-side, but it also means that a user is left waiting to receive any of the HTML that we want to render the page with. That means that things like fonts, CSS, JavaScript all have to wait until we start running a server, which could invoke cold starts and increase the latency of the application. So the challenge here really is, how do we balance the two approaches? How do we achieve the speed of static rendering while retaining the personalization of dynamic rendering? This is where the limitations of these traditional rendering methods become really apparent. Developers are usually left here now having to choose between speed and functionality. But these are the problems, these particular challenges highlight the problems that PPR, or partial pre-rendering, aims to solve, combining the strengths of both static and dynamic rendering methods. Enabling partial pre-rendering is as simple as adding the experimental PPR flag to your Next.js config. Once enabled, pages will be rendering using the new rendering pipeline. It's experimental right now, and we're not planning on changing that for Next 15. And it still does currently require you to install a canary release in order to use it. A little bit of an explainer of what partial pre-rendering is. It enables us to generate a static shell at build time. This is served directly from the edge to browsers, while a request is sent back to the origin at the exact same time to complete the dynamic render, which is then streamed in on the same response. It's really composed of those two parts: the static stream that contains the shell, the dynamic stream that contains all the dynamic data. Getting the static shell to users early is really crucial, as again, it allows resources such as JS, CSS, and fonts to begin preloading and as early as possible. But how does Next.js do it? We're not doing anything super special here. Anyone technically can implement PPR. But how do we do it? Well, of course, we're using React. This little handy pre-render function, during build, we call, it's called pre-render. Surprise, surprise, although it's from a import static edge, which technically the app router is using an edge version of the React implementation right now to support all of our runtimes. But it produces two parts. The first part here is named a prelude, or the static shell. And the second part here is a postpone state. The postpone state is just a blob of JSON, not really important. But really what it's describing is what is contained inside the static shell. So when we're thinking about when we run the pre-render, what's actually happening is that we're outputting a static shell that's of HTML. We're outputting this postpone state that informs React of what parts are contained inside that static shell so that it can resume the render. And that's exactly what we call Next, is the other resume API. React uses the postpone state as a reference to understand what's in the shell, so it only needs to send on the diff of the static parts. This resume API creates a stream that we can attach to the end of the, we could attach to the end of the static shell that's being streamed out at the same time. But the timing of this is critical because it means that at the same time we've started to serve the static shell to users, we're also kicking off the dynamic invocation at the origin, saving precious milliseconds. This means that as the browser is already downloading static resources that were hinted from the static shell via link headers or tags, we're already invoking the server at the origin to render the dynamic parts of that page. Thanks to React streaming, these pieces are sent, swapped with their suspense fallbacks, meaning that we don't even have to wait for hydration in order for the page to load all those pieces. We're truly getting the best of both worlds. The difference from traditional rendering methods here is that when we detect the request data being accessed, we don't actually bail out of static rendering entirely. Instead, we just trigger the fallback at the nearest suspense boundary. In this example, cart accesses request data, and as a result, the cart skeleton will be included in the static shell, having the cart component streamed in via the dynamic resume render afterwards. If no component on the page accesses request data, it would render the entire static page during pre-render. No need for that second dynamic resume render. You get to just write React. It's composable, fantastic. The question is then, how do we detect when you try and access request data? This has been a problem that our team's been working on over the past year, and we made a lot of changes since that time. I'm really excited to share that with you. So last year, when we introduced the partial pre-rendering, we took advantage of the React postpone API. This API actually threw an error when it was invoked, and it's used by Next.js with functions like cookies and headers during pre-rendering. The error was then caught by the surrounding suspense boundary. We assume this approach should work really well because we have other APIs like not found and redirect, which also throw errors in order to communicate user intents. The problem we noticed, though, is that when users tried to access external APIs like database drivers, is that they weren't expecting these operations to throw. This triggered issues like entering retry loops, like you see here, where the fetch failure was expected to have come from fetch itself, not from Next.js patching it. And it attempted to recover using a retry instead. Additionally, user code here is at risk, because what's the first thing you do when you see an await in your application code? It's probably wrap it with a try-catch block to make sure that you handle those rejected promises correctly. Suffice to say, we had a problem with the design. This led to the introduction of the unstable rethrow API, which is still unstable, will probably get removed at some point or tweaked in some way. Lets users write try-catch blocks around application code in order to, and using the unstable rethrow API to rethrow internal framework errors, but not interfere with their application errors that they were expecting. So the unstable rethrow simply is a utility that would rethrow any Next.js internal errors that we were using as signals. This solution introduced, though, a new problem because it required developers to remember. And if there's one thing developers are good at, it's being lazy. Maybe that's just me, but we don't want to remember anything. We're Googling absolutely everything. If remembering was easy, we wouldn't have languages like TypeScript that warn you when you're missing parameters. It's the world of JavaScript. With these types of errors being thrown all over a user's application, we were left with no consistent or reliable way to warn users that they always need to rethrow framework errors. Suffice to say, we needed to change something. Something needed to change. What we needed was a way to suspend the processing of user code when we tried to access request data. Errors seemed like a really good logical choice, but the trade-offs at the try-catch blocks meant that these signals that were meant to inform Next.js about request data being used would actually be unreliable and potentially lead to longer than expected build times due to retry logic. If we can't throw an error, then what primitives do we have left? The answer? Promises. To be more specific, developers are already used to managing promises. And with the advent of React Server components, for the first time, you could write async components, allowing data fetching to be co-located, all while using native APIs that they were already familiar with. So let's take a look at our request APIs. We needed to make these functions return promises. This is really important, as we wanted not just to return an ordinary promise, but a promise that would never resolve during the static pre-render. We had to turn our request APIs from being synchronous to being asynchronous. This also meant deprecating the previously unstable no-store API in favor of the new await connection API. Now, this worked really well for existing APIs like cookies or headers, but what about other I/O? We definitely don't want to patch every API. To solve this, we actually can take advantage of an already built, tried and true scheduling mechanism, the Node.js event loop. Now, things are going to get a little bit technical. And I'm only going to nerd out for a couple of slides, but I promise I'll finish off with a little bit more of a demo and bring everyone back. So, Node.js being a single-threaded application means it can only run one block of synchronous code at a time. This means that when you needed to perform tasks like I/O, it has to offload them to native code. An example of this is when you await a fetch or register a callback for reading a file. Next.js can take advantage of that fact because I/O that's non-deterministic can't complete in the same task. This allows us to do something quite novel. This is a block of code. An interesting one, because what we do at the first thing we do here is schedule a set immediate to pre-render the application, and then scheduling another one synchronously right after it that calls abort in the next task. So what happens as a result of this fantastic block of code is that Node.js will process everything inside the microtask queue before moving on to the next task, so that all microtasks that can resolve within the first task resolve and return immediately. So what that allows us to do is do something quite interesting with request data. But you must be wondering, how do you include external data in your static shell? Data from your CMS may require you a fetch in order to retrieve, and clearly won't complete within a single task of the event loop. What we do is we identify and fill any cacheable entry, which are those annotated with Next.js cache APIs like useCache and even unstable cache. We do this during a prospective render prior to the pre-rendering process, where we fill all the cacheable entries so that during the actual pre-render, when it occurs, it can resolve all of those cacheable entries within the same task because we've already filled those cache entries. In this example, getData calls fetch, which is not cached. As a result, an attempt to render component is aborted because the fetch for the data doesn't complete within the first task. This causes the skeleton component to render instead. We refer to these pages as being partially static. They require an additional resume render in order to stream in the dynamic parts of the data. What if, however, we wanted to include this data in the static shell? Well, this is where we can take advantage of those new cache APIs and add useCache. Adding this here allows the promise for getData to be evaluated within the prospective render and its value to be cached. This means that when we perform the actual pre-render, the value is already available and resolves within the same task. This page is now fully static. These static pages can be served from the edge cache, as they don't require an additional resume render at all. They're fully static. So it allows you to take a page that was dynamic, turn it into partially static, and can become fully static depending on how it's being invoked. It's really cool. So to enable this new mechanism for detecting request data access, you need to add today this dynamic IO flag, as well as the PPR true flag to your config. But I wanted to add a special call out today for APIs that access path name information. In traditional rendering, when a page is requested that we haven't pre-rendered yet, such as a page with a dynamic path parameter, we either have to generate this page at runtime, or we have to, which blocks the browser until the page is rendered, or dynamically render the entire page. Onwards to partial pre-rendering, we have the solution. So in this particular example, the params is actually now a promise as a part of Next 15. So when we pass the params promise into the product details, you can await that. You've probably seen this example in a couple of places already during the conference talks today. But what this enables us to do is something quite special, because if you notice before PPR was enabled, we didn't have anything special about params. Params are just params. You access it, it's an object. But now it's special. Now you have to await it. Something's different. What changed? Well, now we can generate a fallback. The fallback is actually whenever you access params, we can bail out to the next suspense boundary. So it means that for pages where, like a blog or a product page that may actually have a skeleton that's usable, like we saw with the EcoStore example, is that, in fact, what it does is create something that can be served to any page, regardless of the dynamic path parameters that are used, which is fantastic. You get all the benefits just from adding suspense and awaiting those params. So let's take this EcoStore from before and configure it to take advantage of partial pre-rendering. Let's switch back to the demo. So this is the page we had before. We're taking a look right now at the dynamic page, use a dynamic cart and a suspense boundary. Let's open up our next config and hit undo a few times. Return these flags. You might be thinking, what's next? That's it. There wasn't anything special, and that's really what's cool about this, is that if you're already following our data patterns for managing dynamic data, where dynamic cart just simply awaits for its data, it's already just going to fall back to that suspense boundary. Nothing special is required. You just get to write React. That's what's taken us so long to figure out all these particular details. The error throwing sort of messed everything up at the beginning, but honestly, you just get to write React. That's what's really amazing about this. We'll switch back to the slides. So not only was it really easy for us to enable, but it also presents a great experience for our users, as now they're able to experience the site arriving fast and with well-designed fallbacks for data. We simply had to use the language of React and compose the components. For those of you tuning back in after that technical run through here, following the actual building blocks and the patterns we recommend for React Server components, you're already ready for partial pre-rendering. You can enable it in your projects today. Suspense is our mortar, allowing to create stable boundaries for the dynamic parts of the page to be streamed in. Thanks to partial pre-rendering's hybrid rendering approach, we're able to serve the static shell to users as fast from the edge as we possibly can, minimizing the time to first byte and the first contentful paint. Thanks to us kicking off the dynamic render, at the same time, we're also streaming our statics data. We're able to minimize the time it takes to load the request data, thereby minimizing our largest contentful paint. Partial pre-rendering really is the future of Next.js and App Router, but we're not done yet. Today, both of these flags are required to take advantage of these features. While we're not planning on removing the PPR requirement as an experimental flag for 15, what we are planning on doing is eliminating the dynamic IO flag, which sounds kind of confusing, I'll admit. But really what this means is that whenever you use PPR, you're also using dynamic IO. We're just building it in because it's the future. That's really, it just allows you to write React and you get all the benefits. Fantastic. The other one, I've also talked a lot today about this single streaming approach, where we have a streaming static shell, we attach to streaming dynamic HTML. There's a bit of a problem with this one. Today, it's only supported in Vercel and that $5 VPS. That's right. Self-hosting actually also supports the single streaming approach. Our commitment to open source means that that was one of the first things we implemented as a part of this design to make sure that it works successfully. But I have some more good news. CDN support is coming. What this means is that once PPR is stable, we're planning on making this feature compatible with other CDNs. I don't have a lot of details to share yet. A little bit of a teaser is we're planning on making some additional pre-render and resume mechanisms that would allow CDNs to serve and cache pages rendered using partial pre-rendering. In conclusion, partial pre-rendering represents a really significant advancement in the advanced application rendering strategies, offering dynamic at the speed of static. Understanding how PPR works may not have been necessary, but I hope you enjoyed the deep dive into the engineering behind its development. This has been a passion project of mine for the past year. I'm really just excited to have shared it all with you all. Thank you.